And so we have arrived at week 12 and the final topic of this course, eigenvalues and eigenvectors. Sometimes this topic is called diagonalization of a matrix, and we will see how the two are related. Now, to properly motivate this particular subject, it helps to have seen differential equations, and that's not a prerequisite for this course. So we're going to be a little bit limited in how well we can motivate the topic, but we'll do our best. Our goal is to make sure that you understand enough so when you need eigenvalues and eigenvectors in your further studies or in your professional life, you will have the ability to quickly acquire the necessary additional skills related to this topic. We're going to motivate this week's topic, how to compute eigenvalues and eigenvectors of matrices, by looking again at the example of predicting the weather with a Markov process. We're having a flashback to week 3, and this is a table that tells us for any day of the year what the predicted weather is for the next day. Now we took that table and we used it to create 3 equations that told us how to compute the different probabilities for day k plus 1 from the probability of different kinds of weather on day k. So here we have those 3 equations. And what we saw then was that we could set this up as a matrix vector multiply to get from the state on day k to the state on day k plus 1. And we could just write that as the matrix P times the vector x super k for the vector of different probabilities for day k, creating a vector x super k plus 1 for the state vector for day k plus 1. So these vectors x were the state vectors, and the matrix P was the transition matrix. And the important thing about matrix P is that the entries in each column add up to 1, and obviously they're all positive values because these values have to do with probabilities. How did we express that today is cloudy? Well, we did that by setting our state vector x0 to the second unit basis vector. And by now, the unit basis vectors have become your friends. So if we want to then predict what the probability is for tomorrow's weather, we simply multiplied the transition matrix times the state vector for today. And if today is cloudy, then we get this. And if we multiply it out, we notice that we simply pick out the second column. And that's a property of multiplying a matrix times a unit basis vector that we've gotten to use many times in this course. Then if you want to get the state vector for day 2, you multiply the transition matrix times the state vector for day 1, and you get this right here. We then asked the question of how to predict the weather a week from now, and we learned that we can do that. And indeed, you went and you did an IPython notebook in week 4 that did just that. And this, we claimed, was an example of a Markov process. And if you look on the discussion board for this course, you will see that there are discussions on different examples of Markov processes. Now, if we start with a state vector for day 0, then with this model we can create a state vector for day 1, for day 2, day 3, day 4, and so forth. And here's the vector after 7 days. And what's important here is that the vector doesn't change that much from day 6 to day 7. And if you did the notebook and did the part of the notebook where you were asked to do this for a whole year, you notice that the state vectors after a year really don't change at all anymore. We are in what is called a steady state. Had you started with a different vector, here's just some random probability vector, then, and you went through the same exercise, then again, after about a week, you end up with roughly the same vector. And if you had kept going for a couple more days, then you would have noticed that it doesn't appear to make any difference with what vector you actually start. So what's going on here? What's eventually true is that the state vector for the next day is the state vector for today. So the vector simply starts repeating itself, approximately. So that leads us to the question, is there such a vector such that p times x is equal to x? Because that would give us a vector that would describe the typical weather. And then if we started by picking our first vector to be that vector x, then notice that the vector for day 1 is the same as the vector for day 0, and so forth. In other words, if we start with a vector that describes typical weather, then if from that we start describing what would happen in subsequent days, we would simply keep getting the same vector that describes typical weather. Now, this is an example of what's known as the algebraic eigenvalue problem. And how can we describe that? Well, it's described as ax is equal to lambda x. And notice that x is a vector here, and lambda is a scalar. Now, if you think about this for a second, the output of a times x has to have the same size as x does. And therefore, inherently, when we talk about the algebraic eigenvalue problem, A must be a square matrix. Otherwise, the whole idea of an eigenvalue or eigenvector doesn't have any meaning. We start with a square matrix A, and what is to be computed for this matrix is eigenvalues lambda and eigenvectors that are not the zero vector that are associated with that lambda. Now we're going to see that those eigenvectors are not unique, so what we really are interested in are ways of describing the infinite number of eigenvectors that exist for each such eigenvalue lambda. How do we relate this to our weather example? Well, we were interested in px equals x, so here P is a square matrix. It happens to be 3 by 3. And what we would like to compute is the eigenvalues of lambda. It certainly seemed like there was a vector such that p times x is equal to x. So what does that mean? Well, if that's really true, then lambda equals 1 must be one of the eigenvalues. We're going to see that typically there are actually n eigenvalues if the matrix is n by n. And notice that in the process of computing the prediction for many days from now, we actually discovered a vector that seemed to have the property that px is equal to x. As a matter of fact, if you go back and you look at the output of your IPython notebook, this was approximately the eigenvector associated with lambda equal to 1. So in summary, computing eigenvalues and eigenvectors of a matrix is a very important topic. It's a topic that we're not going to be able to do justice in this particular course. You're going to see a lot of examples of where these are important when you take a course in differential equations. So we're only going to have time to scratch the surface. However, what we hope is that the background that we give you will allow you to then more quickly understand the topic when you see it in other classes.